It's my pleasure to introduce our second keynote speaker, and Simon Sim. His name is probably familiar with many of us because he has a long-time contributor in our FPGA field. He held various kind of positions at the Google, Facebook, Microsoft, and the Xilinx. He worked on such a wide range of topics where few of us can actually match, including functional programming, domain-specific language such as Lava, compilers, customized hardware, acceleration with ASICs and FPGAs, formal verification, configuration management, distributed system, Kubernetes containers, and also cloud computing, and even low-level Android performance improvement. He also had academic positions at the University of Glasgow and University of Birmingham. His latest appointment is a fellow at the Groq, and I'm looking forward to hear that both about the company and his latest adventure. With that, welcome, Simon.
Thank you kindly for the introduction. Greetings from my mother's living room in Scotland. So let me see if I can project my presentation, I think. Okay, so, right, can people see that? We've got the first
Yes.
slide? Great. So I very recently joined a startup company called Groq. I've not been here very long, but I'm going to do my best I can to try and represent what our company's about. And I'm very excited to be at its company, and it does a lot of exciting things, which remind me about what excited me when I first got into FPGAs, and it has many things in common with FPGAs. And one of the messages I hope to get across today is that I think that architectures like TSP, which I'm going to describe, are actually very good to be used with other kinds of compute devices like FPGAs and help to solve end-to-end problems in areas like machine learning. So what is Groq? It's a kind of a startup. It's founded by 2016 by someone called Jonathan Ross. Jonathan and I both worked at Google at the same time, and Jonathan was one of the people that really helped to design and create these Google's tensor processing units. There was at Google there was a need to make special chips to accelerate machine learning, a scale and efficiency and energy consumption and price that was more reasonable than what all the alternatives were. So that's why Google started to create these special chips, which many of you I'm sure have read about. And then Jonathan went off and founded his own company to pursue his own vision of how TPUs should be made. And just a few months ago, I decided to join him in his efforts. The company's headquartered in Mountain View, but it's got a policy of hiring people anywhere in North America and maybe a few other places with exceptions. We've got one person in Cambridge, England. But we've got quite a large team in Toronto that works on our compiler, and a kind of growing team, in Seattle. It's pretty well funded, and we're kind of accelerating at an exciting rate. What the company makes is a silicon chip designed for machine learning. You see the chip there. That's on the board, and you can buy a card. You can buy a node that's got several of these cards with chips on them, and you can get a rack, so you can access the compute at very different levels of kind of different levels of performance and capacity. So I'm going to represent what Groq makes as a company, but I will probably do it through my lens and my view of the world, which is forged by two things which I've always tried to marry in my life. One is a kind of programming languages, formal methods, semantics, mathematical kind of view of the world. And that's led me to use things like the Haskell programming language to try and make tools for either for programming things like FPGAs or other kinds of accelerators, or even for designing them. And my other love has been FPGAs, I won't tell you what the chip on the right is, but it's the very first FPGA that I used. And I was just, what excited me was the ability to make the perfect architecture for executing my algorithm. I could design the perfect memory hierarchy, the perfect data path, have it laid out exactly on the chip as I wanted to. And when it ran, I knew cycle by cycle exactly what I would do, what the memory accesses would be like. I had complete control over how much data and how data was recirculated and calculated on the chip before it was evicted out to external memory. And that was very that was very exciting. And what the function programming let me do was give me a high enough level programming model to let me do low level design. So the kind of the diagonal that I've always been interested in is high level techniques for low level design. I always say that this is like a missing diagonal in our field, because if you look at computing science, electrical engineering in general, we seem to have a lot of techniques for doing high level languages for doing high level programming. Java for doing apps, for doing your web apps, and low level languages for doing low level programming, assembly or C, or for systems level software, or VHDL Verilog for RTL circuits. But it's this diagonal, I think, is a really powerful thing. If we can come up with higher level tools that make experts more productive at producing low level high performance systems, I think we solve a lot of problems that people that people care about. The way this all happened was kind of by accident, because in my PhD, I developed these kind of functional programming tools for doing hardware design. But in the abstract, I wasn't thinking of any particular chip or any particular technology. And some of you will know of John Gray, who with Tom Keene co-founded a company called Algotronics in Edinburgh. And I had just started as a new lecturer at the University of Glasgow, having finished my PhD on how to use functional programming to do chip design better. And John had known me from previous projects I'd worked on him. So he drove over in his car from Edinburgh to Glasgow. And if you know anything about Edinburgh, Glasgow politics, you have to be pretty desperate if you're going to drive from Glasgow to Edinburgh. And he barged into my office and hit me over the head with a card of these chips on it, which they had designed. And he said, "Right, Satnam, we've made these chips, we think they're fantastic. Work out how to program them. I'm coming back in 3 months. Let me know what you've done." And he disappears. I start my career about how to program these low-level systems with high-level tools, which then led on to things like Lava and all my work at Xilinx. So that's how I kind of got into this field, by trying to apply high-level techniques to low-level design. And what's happening at Groq is just the same thing again, just for a different type of technology, with different kind of granularity, with a different application domain. So Google makes TPUs, Groq makes TSPs. These things have got much in common with FPGAs, and I think when we can use the two together, I think we can do great things. So what's common between these two things? Well, one concept from the title of his talk is determinism. Often when we design circuits for FPGAs, we know cycle by cycle what we're going to do. We've crafted a data path with pipelining and laid out every gate, and we know exactly cycle by cycle what's going to happen. And that's something that's the TSP chip that Groq makes has a similar property. When you have compiled your TSP program, you know exactly how many cycles it will take to execute. It's known at compile time. It's not determined is not determined at runtime. Another great thing about FPGAs is spatial computing. We can create many copies of things, rows and columns of things, and put them across our FPGA to get lots of parallelism and pipeline across them, etc. That's one of the great ways we get amazing performance from FPGAs. And the TSP architecture has the same thing as well. It also lets you do the same spatial compute optimizations, tricks, and implementations that we can do with FPGAs as well. Another thing that benefits our FPGA circuits is having memory distributed across the chip in block RAMs or in other memory units, so that we've got many places where we can simultaneously at the same time access memory, compute, and write back to memory. And that's another property that the TSP shares as well. Where it diverges from FPGAs is granularity. So the processing blocks inside the TSPs are much larger, so they're much coarser grained. FPGAs give you phenomenal amounts of freedom. Every lookup table can be doing something different from every other lookup table. So in the TSP architecture, you can think of it as being more like a VLI-W architecture. You can think of it more as being one processor that's got many parallel characteristics to it, rather than many small parallel things that you piece together as you wish. But despite that, there's many things that are common about both of these ways of computing. So, if I wanted to make a convolver, I can look at my equation and I can decide I'm going to make it by using several multipliers and adders. I'm going to use some registers to do some pipelining, and I can run this, implement and run the circuit, and I know exactly how many cycles it will take if I implement it on my FPGA. And if you were to implement it on TSP, you would also know exactly how many cycles it would take. We know we can access memory, and we know cycle by cycle how we access memory, how we compute with those values, and how we write them, how we write them back to memory. Furthermore, we can lay things out exactly as we like. One of the things I worked on in my past life was how to describe circuits like convolvers and so on for FPGAs, such that you can actually control the layout. Because you in your mind might have an idea for a good layout, and if you can lay things out close to each other, then the tooling can then find a good route between the components. And so here you see the layout of some filters, and then you see the wiring pattern below, and that it looks nice and regular. And certainly back then with the FPGAs from that era, that actually gave you a performance win. I think I would probably confess to the fact that these tricks maybe don't get you as much advantage today as they did then, due to advances in FPGA architecture. And the inspiration from it all then comes from mathematics and forms of representation. Can you come up with the right abstractions which quintessentially get to the heart of what you're trying to do? So for circuit layout, what didn't work was trying to compute XY coordinates for every lookup table, so you could compute the RLOC value for every lookup table registers. That was not a tractable, scalable way of programming. So there we were able to look at other places, like, for example, Escher's beautiful fish drawing here, which actually has a nice recursive algorithm behind it, and a formula. It could be created with a formalism called functional geometry, where you can lay out tiles and rows and columns and rectangles, and rotate and flip them, and you could just write a small number of lines, and then you evaluate it, and you get this beautiful drawing. So we took the same ideas, which let us systematically produce Escher's drawings, and we applied them to circuit diagrams. And we came up with a semantics for circuit composition, which composed not only behavior, but also layout. And when you could do that, you could write descriptions which compose layout and behavior. So in the past, we did work like describing these sorter circuits as batches by tonic merge sorter. You describe it in Haskell, which is what you see at the top of the screen. If you look at the right, for somewhat old FPGA, you see that the layout that it produces. So every single lookup table coordinate has been calculated from these geometric descriptions of these butterfly networks. You know what is to the left of what is below something else. So that's what I mean by this missing triangle. Can you come up with a high-level way of describing something that it really is quite a low-level thing that you have a lot of control over, because you care about performance or area or power? And we're still playing these tricks again and again and again, except now in a different space. So what I'm going to do now is I'm going to describe our chip architecture to you, and let's see which things hark back to inspiration from FPGAs and which things look different. And a key bit of inspiration for the designing these chips was the notion that we should route tensors and not packets. And by tensors, as an approximation, you can just think of that as being vectors, as being matrices, or matrices over time. These are the values, the inputs we're going to pump into our machine learning algorithms that we implement on our TSP. And since I'm in Scotland, I'm going to give you a clue about exactly how we
Classic,
kind of
synonymous
drew
with
inspiration.
celebration.
This is
The
one of my
dashing white
favourite
sergeant.
dances. I grew up in Scotland in school when
To
we
begin,
taught Scottish
dancers
country
form
dancing.
up in lines of
And,
3, forming a
so we all
circle,
had to do it
8
as part of
steps
the
round and
But
back.
what's really
The centre
good about
person in the
Scottish
line
country
faces the
dancing
dancer on
is
the
that
right,
it's
sets to
it's a
him or
totally
her,
deterministic
then turns with
synchronous
both
thing. There's
hands.
various people doing
The dancer then
competitions,
turns and sets to
and,
the other person in the
everyone
line.
is just doing their
Again,
own
the
thing, and they
2-hand
all
turn,
arrive
followed by
perfectly
reels of 3. A figure in
musical
so many Scottish
competition,
country
some
dances.
data exchange,
The
they
dancing
go
couple
off,
giving
and
left
then,
shoulder to the person they are
and
facing.
intersect with
As the
next
lines of
set
3
data.
reform, you
So
have
the-
time to
so
draw
the
breath before sweeping
there's
through
no
raised arms
waiting,
to
there's
form
no
another set,
arbitration, there's no
another
arguing
circle.
the cycles.
The dashing
All
white
just
sergeant,
works,
with its very distinctive
all
tune,
just works
is sent.
nicely. And I think at some level of abstraction, what's happening in the TSP chips is rather like Scottish country dancing. So, so what are so this is what you see in the middle is the chip. What's on a chip? In the middle, there's a vector unit, and that's used for various vector, mainly vector operations. To take like a 1D matrix, to take one vector and add it to another vector, to multiply it with another vector. So it's a whole series of things that you can do with vectors. So the middle of the chip is dedicated for that function. To the left and right of the vector unit, we've got memory. But the memory is not monolithic. It's divided up into slices. So there we can see, a bit of a connection with what we might have in FPGA, where we might have DRAMs or other larger memory blocks on FPGAs. And then on the edges of the chip are matrix multiplier units. And there's effectively there's 2 on the left and 2 on the right. So you effectively have 4. So that's the basic structure of the TSP chip. So how much memory we have? We've got 220 megabytes of memory, and that is split up into things called slices that we'll talk more about. There are 4 matrix multiplication engines which do a fused dot product. So this will be a 320 by 320 operation when the element type is integer 8, but the multipliers work over floating point, 16-bit floating point values as well. We've got 5,120 vector ALUs, so these can perform multiplications, additions, ReLUs, many of the common operations that you would expect to find when compiling a machine learning algorithm. The chip's got vast amounts of memory bandwidth, 480 gigabytes. And the chip's designed so that you can snap them together in kind of Lego style. So there's a chip-to-chip interconnect, which lets you maintain this deterministic synchronous compute model across the barrier from one chip to another chip. You can't quite see it in this diagram. We'll see a little bit more about it, but we've also got we've got 2 data switches, which let us take these vectors and reorganize them and permute them in various ways. And this whole thing is driven by a whole bunch of VLIW-esque instruction queues, which tell machine on each cycle what to do. So that's a high-level view of what's going here. So there's 2 key architectural design decisions to be aware of. One is we have a streaming data flow model. So each of these operations are having data streamed through them. So they're standing still. They're not saying go to some arbitrary memory location X and read the value there, go to some arbitrary memory location Y, read the value there, do some compute, write to some arbitrary location Z. They are constantly being fed streams of data. They compute over them cycle by cycle, and then they write the result to an outgoing stream. And that's another kind of connection that you would have with many of the ways we would implement algorithms on FPGAs as well. And the other thing that's characteristic of this, distinctive characteristic of architecture, is we've got a disaggregated compute model. And we'll see a little bit more about that later on. So from a practitioner's perspective, what are the key ideas? What were the kind of insights that led to this particular design and design choices? So one was I feel that ALUs are relatively inexpensive. What it really costs is feeding them, right? Wires at full bandwidth are very expensive. And I would say that's also something that is, I would guess people in FPGA world have a similar perspective as well. So why does this hurt? It's because wires don't scale as well as transistors. And we wanted to focus on extracting as many deep learning ops from the CMOS transistors that we have as possible. So that was one guiding principle. The other thing we cared about is something called batch one performance for low latency inference. So for machine learning workloads, one good trick we can often pay is we can do batching, right? Rather than give the machine one problem to solve, we get together 1,000 or so problems, and we send them in one go. Some computation is done, and we get results back. And this lets us amortize some of the cost of sending data and receiving it. And for large batch sizes, this architecture does very well. But this architecture is also designed to do very well with small batch sizes, and that becomes very important for machine learning workloads that are interactive. So things like a chatbot, etc. So that's a situation where you have a low latency requirement for your machine learning algorithm. You've got one bit of data, you need it to be processed right now, and you want that round trip to be as quickly as possible. So we've designed the architecture to try and be good for batch performance. And at various, we've designed systems which involve chips, which involve cards, boards, and racks. At each level, we want to try and exploit locality as much as possible, whether it's to do with the design of how we lay things out on the chip, or how we do the chip-to-chip interconnect, or even how we then put cards together in racks in racks of systems. So the idea is to have a glueless multiprocessor system. So what are the things that are on the Groq chip? We've got memory, and that implements the load and store operations, and we also can support various kinds of gathers and scatters as well. And it works in bytes or any type, that could be mapped to bytes. It has matrix multiplication, which does matrix multiply and convolutions. And the input types for it are 8-bit integers and 16-bit floating points. You can have 32-bit floating point values, and the system will consume them, but it will break them down into 16-bit multipliers, and by software, it will emulate a 32-bit multiplier with some compensations to try and not lose too much position, and then rehydrate a 32-bit value at the output. So in your TensorFlow or your PyTorch Python programs, you can still write computations with 32-bit values, and they'll go through the compilation tool chain, they will run on the chip, you'll get your result back. So it'll look like as if it was done like a 32-bit native floating point calculation, but under the hood, it would have been converted to a series of 16-bit operations. We've got switch execution units, and these are used to transpute, permute, and perform kind of inter-vector data flow operations, and they operate over any types. And then we've got the vector units, which perform element-wise operations over vectors, all the things you'd expect: addition, multiplication, comparison, various kinds of casting, square roots, ReLUs, etc. And then other operations that are very common in machine learning, like softmax or einsum, they're all done by translating into the primitive elements that our chip actually implements. So that's all done transparently by a compiler. So to understand how this chip works, one good thing to do is to take a horizontal slice through the chip. That's kind of orthogonal to these vertical things that you see. Because all the action for a particular computation occurs within one of these slices. So data is going to move along this slice, left and right, and get worked on. It will start from a memory. It then might go to a matrix unit, and then it might work its way backwards to the vector unit, and then it might get written back to a memory. So that's what's happening each one of these rows. So and the instruction set that's fed in is going to determine exactly how things move forward and backwards within this role. And the way you get performance is by trying to do as much work as possible for each read you have done. So as soon as you read when you read some data, can you keep performing operations on it in the VXM, in the MXM, in SXM, before you have to write it back to memory? And the more you can keep data in flight and working data, the better performance you'll get. And I think that perspective is a very familiar perspective for people that work on accelerating things on FPGAs. So here is so here's that same slice, but I've shown you the extra the z-axis dimension there. So you can see the matrix multiply on the left, data manipulation in SXMs, the memory banks, element-wise VXM in the middle, and then the map-mul on the right-hand side. Key concepts are, it's a heterogeneous architecture. You've got these, if you go left to right, you've got different processing elements. Like FPGAs, it's a spatial computer architecture. You can view it as a spatial in 3 dimensions. One dimension is the functional slices, these heterogeneous slices that you see there. The other is SIMD parallelism, and then the other is other data streams. So the operations data which chain together return to memory. That's how you get lots of performance. And every transaction is deterministic. We know at compile time how many cycles that they will take. The other way we get determinism is that all the distributed memory, it's SRAMs. So there's no caches, there's no buses, there's no arbitration. So just like on FPGA, you could build a deterministic compute machine using block ramps, etc. We can do the same things. We can do the same things on the TSP as well. Okay. And so how is the memory broken down? Well, memory is broken down into 88 independent slices. So the chip is in 2 hemispheres. So there's 44 one side and 44 on the other. So this memory's got 1,892 addresses, and they're arranged in these quad timing groups. You can read and write 1 physical stream per cycle from two banks. So you've got so that means with 64 streams at full bandwidth, you've got 80 terabytes per second. So you just have this, stepping back, you just have like a large amount of bandwidth on these devices. So if you can keep everything busy, then you could do phenomenal amounts of compute. So this picture shows you an example of an operation where you would read from memory as step 1, do something in step 2 in the VXM, do something in step 3 in SXM, then do a matrix multiply in step 4, and then step 5 you finally write a result back to memory. So if you can do that, then you're in good shape and you're making good use of the available resources. So what do we have on the chip? We've got 220 megabytes of memory that's split up into these 88 slices. We've got 5,120 ALUs, each with 32-bit wide operations. We've got an SXM, which is shift, rotate, permute, and distribute. And we can use that to do things like scatter and gather. And then we've got a matrix execution module. And when that's going at full tilt, that can do 409,600 multiply accumulates in 8 mode. I mean, you do FP16 along one of that axis, you're going to have that number. The programming model is a stream, it's a producer consumer stream processing model. So we're not reading and writing from arbitrary registers. We're just streaming data as quickly as possible through each of these ELUs or MXMs or SXMs. The streams run in two directions. So some will run eastwards, and some will run westwards. And the streams each have names. So you can tell from the name which direction that they're which direction that they're going in. So maybe I shall skip a few slides, maybe not go into too much detail, but this shows how the streams are named, right? They have lanes and stream numbers and a direction of flow. So maybe I can show you. Yeah. So the basic data items we operate on are scalars, vectors, matrix, and then tensors. And anything that's higher dimensional than that has to get reduced to something that looks like a rank 2 tensor. And the MXM forms a 320 element fused dot product. So those are the data types of the lowest and the highest position. And internally, we use something. We do some special special circuitry to try and retain as much precision as possible. So something called true point. Right. So what are the goals of the on-chip network? Well, one was to try and exploit abundant on-chip wire density. Another was to have a topology that matches the kind of parallel algorithms that we expect to get from machine learning workloads. And we were quite aggressive with how far could we get, with each of these vertical chains, how far could you go over, what could the timing on that, what could the timing be on that? And we were constrained by the usual things, by the die, the wire density we can get on the particular architecture that we used, and then what the implications would be for reliability, manufacturability, and for yield. So this is another view of the picture that you saw before, but we've turned it around and cut into it to get an orthogonal slice. What we've done is we've rearranged the functional units each into the different slices, disaggregating the cores across the entire chip. So each row of the 2D mesh represents a cross section of each of these cores, and then there's a control logic which then generates the ICUs that generate the instructions that are fed through. So you can see in this slide here that the data flow moves left and right, and the instruction flow is vertical. Okay. So the two dimensions of tiles are X dimension, that's where the data flows, and then Y dimension with control flows. The streams are ECC protected, and we've got 144 independent control units that are driving the functional units, telling them what to do. So let's look in detail at one of these units, the VXM. That's the vector unit. So it's got, like I said, operations like add, ReLU, etc. And you can, VX is made of ALUs. You can see the 16 ALUs there, and some are large and some are small. So some ALUs have got a wider selection of operations like trig operations, and some have got a subset of those operations. This just lets us be more economical with area. So this is a zoomed-in view of one of the VXM tiles with a lane coming in from the west and a lane coming in from the east. And the ALUs are colored differently depending on whether they're a large ALU or a small ALU. And a very important thing you can do with ALUs is you can chain them together so that you don't have to, after using one ALU, leave the VXM and either go to memory or go to the next unit. You can actually keep recirculating around this tile and chain together many operations, which then gets you a significant performance advantage. So then how would you program one of these chips? Well, one way, and the main way we hope, is that people will just write in one of the formulas or models that they know about. So, for example, you could use PyTorch, and here's like a completely trivial example of a PyTorch program that just adds two vectors together. So the class here takes X and Y, adds them together, returns them. We create a model out of this, create some dummy inputs to help generate a netlist, and we generate an output graph called Onyx. So ONNX is going to be a data structure that represents the graph that we then want to implement on our chip. And that's one of the, it's a common graph representation that's used in PyTorch. It's one that's actually designed, it's an open source format that's designed by Microsoft. So the compiler we have reads in ONNX files, which you generate with PyTorch or a variety of other ways. And it takes these graphs, which are basically linear algebra operations, and tries to schedule them to execute on our chip. So we'll try and create this static schedule, this deterministic execution plan for these computations. So for that program there, this is the very simple ONNX graph that gets generated. It just got one computational node in it with add, and it takes in a 4-element vector, gives you back a 4-element vector back. You can look at the ONNX file. It's a protobuf, so it's a binary, but you can write out a text representation of it. And if you did, you'd see that the only node in there is called an add node that takes X and Y inputs, performs an add on them, and generates the output. So that's what our compiler consumes. And then that's what's going to then run these vectors, the inputs, the matrices X, Y, and the results. They're going to go sit in these streams as input streams and output streams, and be ripped through one of these super lanes, these columns of the TSP. And there's one of the tools that you have is something called GrokView, and it's a viewer which lets you step through and simulate how an execution might happen. So for that thing that we just saw with A and B, they will be read from memory slices. So the A is being read from one memory slice there in orange, B is being read from another memory slice there in orange. And then they get moved to the VXM that you see in the middle there. That's going to do addition. So that red in the middle shows A and B being added. And then they're going to be sent to another memory slice. Here shown as C in cyan and stored there. So that's what would after compilation, once you execute on the chip, that's what would happen for that very simple example that you that you saw there. So on the x-axis, heterogeneous functional slices, on the y-axis you see time. But let me show you an example of an actual animation of a more realistic example. So here you're seeing a machine learning example where data is being read from the memory slices. It goes up to VXM, gets processed, MXMs on the edges, it gets processed. It goes into the middle and gets processed further in the VXM, and then it's going to, when that's finished, it's going to go back out and get written back into memory. So this fanning in and out pattern that's a very common sequence that you see for realistic machine learning applications that get mapped to a chip. And this animation you can do as soon as you've compiled your program. You can run this animation because we don't need to necessarily the chip. We don't need to run it on a chip and get a traceback because we've got a deterministic static schedule. At compile time, we know exactly what's going to happen on the chip. Let's go on to the next slide. So let me just illustrate a little bit more about what can happen with chaining. So often we want to take several operations, chain them together in the VXM without touching memory. So you might get the result in from matrix multiply, do a bias add, do a ReLU, do a conversion to floating point, and all of this can be happen inside one of these ALU modules. So here you see an example of that where the A is getting the result but in from a matrix multiplication, and its output goes into another ALU, which was, but I can't remember what the B is going to perform. That's going to perform the bias add on ALU 6. Then the final there's a final cast. There's a ReLU and then a final cast to FP16, and that all happens in one operation. So when you can do a chaining like this, you get very good. You get very good performance. I showed you a very simple ONNX graph, just one node in here, but this is a graph of a fragment of one of the actual machine learning models that we work with, which is significantly, which are obviously significantly more complex. And these will contain things like convolution operations and matrix multiplication operations. And our compiler will take this graph, which contains no information about how many multipliers you should use and how many things you can do in parallel at the same time, and analyze it, and then work out how to map this onto map this onto a TSP chip. Somewhat so. So that's a kind of a fairly challenging problem. Again, in the same kind of domain of what we'd expect when we write higher level HLS code and try and map it to our FPGAs. So that's one. So this picture shows a view of the developer stack. So we support PyTorch that goes through this kind of ONNX flow, or anything else that generates ONNX, and TensorFlows as well, by translating it through an ONNX path. However, sometimes you want to have direct control and be able to use this particular ALU and use this particular multiplier and put data on this particular stream. So we also have an API called Groq API, which is a Python library, and that really lets you explicitly control every resource and say exactly what you want at what time cycle. So when you want to have absolute extreme performance and get every cycle of performance out, you can program directly against the architecture, just like you would do with an FPGA when you are saying exactly what lookup table you want and what VRAM you want and where they're located. So you have that power of control. But in other occasions, when the compiler is going to do a good enough job for you, you can just write in Python or whatever else you like, and then there's a path. It's a compilation path that'll map to FPGA. So the Groq API gives direct access to all the hardware resources, the function units, and the streams, all aspects of how the program executes, and then you can also simulate it as well. And by simulation, at simulation time, you'll know exactly what will happen at runtime. And there are layers of higher and higher layers that you can use on top of Groq API, where it will make it a little bit easier. It will let you leave some things unsaid, and things would automatically, to some degree, get mapped to resources. So you can think of it as being a kind of intelligent macro assembler. So today, those are the two ways that you could program a chip: for extreme low-level control for Groq API, or for the majority of cases, you just write one of the standard machine learning frameworks, and we have a compiler that will consume ONNX and then lower and compile and optimize and map it to one or even multiple TSP chips. So the Groq API can take, you can describe several components, A and B, and it will analyze them and generate the ICU instruction control for implementing and executing each of these components, and it will try and merge them if possible and overlap them. The other component that you saw was SXM, and this is what lets you permute operations, lets you translates, rotates, shifts, and there's two of those. Those on each side, and we have a fairly general switch which lets us perform these permutations, and those are, especially in HPC applications, these turn out to be quite important and heavily used operations. We can see some examples of the permutation there. And the big workhorse that on the edges of the chip is a matrix multiply unit, and for integer 8 operations, it'll do 320 by 320 of a density of 2 MXM, and then for float 16, all on one dimension, you're down to 160, and then we can emulate float 32 in terms of float 16 in a way that's transparent to the user. And so what we have is, again, there's a split up of hemispheres, and you have two in each side. And we have special tricks for dealing with how to handle weights and activations and be able to quickly switch between them. So it's done in a way which lets us be able to, on our architecture, support both model level parallelism as well as data parallelism, by being able to quickly switch from one to the other. So, in summary, what we have is a 2D mesh of ALUs, a fairly general on-chip switch, and then 4 fairly large multiplier units for doing fused products, and data streams. So horizontally, control goes vertically. That's what's on the chip. So beyond a single TSP, you can connect several of them together and make multi-chip networks and have racks of these things, and still stick to this model of determinism. So in the interest of time, I'm going to just show you a few pictures, because so this shows you a card. So a card will have a single TSP TSP chip. A card can then go into a node where we have 8 of these cards, and then we've got various ways in which various topologies we can use to connect these together. And then each of these nodes we can stack up and put into a rack. So this is what lets us handle very large machine learning problems, which got many parameters that require way more SRAM than we have on a single TSP. So this shows that we've got various ways of connecting things together. We can either have 2 4-way TSP groups or 1 8-way TSP group, and this is all software. This is all software programmable. So I'm going to actually, in the interest of time, skip forward, maybe not say too much about these. And then we also have a synchronous protocol between chips, which then lets us communicate and then keep the synchronous deterministic computational model that's based on a request responder model. And there's a protocol behind this which drives the C2C links. And this shows the various ways in which we can organize the 8 cards. So there's 8 cards in one of these nodes, and 2 processors, one for the left side and one for the one for right side. So determinism was the word I kind of focused in abstract and in the title, and that's, I think, a very distinctive aspect of this type of computational device compared to other devices that you could have used. So one is we know exactly what's going to happen at runtime, cycle by cycle. So what does this buy us? Well, one thing I think it buys us is the ability to compose things together and make larger systems, so we can use time as an implicit coordinator rather than electrons. But also it lets us know things, be able to estimate power consumptions, because if we know what activity is happening on what cycle, we can then decide to spread things over time in order to manage our power consumption. Or if we know that certain units are not used for a certain period of time, we can pare down parts of the chip. And that's one of the kind of advantages we gain by having determinism and knowing at compile time what the execution plan is. That's what we would find it impossible, difficult to do if we had a model that involved arbitration or buses or caches. Then you don't know exactly cycle by cycle what's busy when. So what are the distinctive aspects of architecture? So one is our focus on quantization. So we don't do, in particular, on int8 and FP16. So we've decided, in particular, to be very good for inference, and since there are many inference jobs that work very well with quantized data. We internally created a special mechanism called TruePoint, which lets us not lose accuracy. We've got predictable execution through deterministic execution, and with a synchronous computing model, we take aim on tail latency. It's something, because we know cycle by cycle we have. It's not something that we suffer from. So the programming models, PyTorch, TensorFlow, let's say JAX or DEX, etc., ONNX, that's where the current focus is, along with the low-level programming model of the Groq API. But what we need are higher-level programming models, things which work in the application domains of what users care about. And I hope that can be something we can partner with other companies and universities to do. We also need to make end-to-end systems. From the user's perspective, that part of that Onyx graph running in a TSP very quickly, that's great, but that's not just the problem they've solved. The user has some image or some chatbot request. They've got some problem they want to solve. So there's a whole sequence of things that happen to do with getting the data from the source, streaming it, dealing with embeddings, etc. So a realistic system involves a composition of processing elements. And I think that's one place where I think FPGAs can play a great role, because there are many types of computation in the pipeline that FPGAs are very well suited to. Some things that the CPU is pretty well suited to, and some things that TSP is suited to. So what we really want are models that deal with the entire end-to-end flow that the user cares about. Can we come up with a set of tooling and models and programming frameworks that solve the whole problem end-to-end, and not just the how do you make this particular Onyx graph go fast. I think there's a need for dynamic analysis tools to be able to help estimate power and performance, and also for static analysis tools which can reason about things like position, and perhaps to do things like correctness as well. So what the advantages in that determinism are bring to us? So I've wondered about determinism in the widest sense. Where does determinism occur in computing science? What advantages does it give us, and where does it cause problems? So we certainly have people worry about determinism at a level of machine learning models, and so there's a fairly recent paper where people look at how deterministic these ML models are, and how determinism can be used to reduce social noise. So that's a very different kind of determinism that we're talking about on a chip, but conceptually there seems to be a problem with determinism that's solving there. We also have determinism at the programming language model as well. And this has been studied quite a lot by Edward A. Lee at Berkeley, and who's gone on to make quite interesting, elaborate models of computation which try and connect together different models, synchronous data flow, all kinds of things, and try and model real-world complex systems by composing together different modes of computation, some of which are deterministic and some of which are not. And I think there's been a great observation about this kind of work by Stephen A. Edwards at Columbia, who says that determinism can be thought of as an abstraction boundary that delineates where control is passed from a system designer to an implementation. So I think that's quite a kind of profound view of the system, because if we could come up with the right contract, the right API, where one party codes and designs models to this deterministic interface, then the other party can take it from that point and then perform all the optimizations and packings, all the things it knows about the details of its own architecture that it's tuned for. So in certain situations, that seems like a very good contract to have. Determinism, of course, is at the heart of the HDLs we use, like VHDL and Verilog. They're designed specifically to be deterministic. It's something that we require about them. That's what lets us design digital circuits. So what's great in the case of the TSP is that we can schedule operations. We know what they're going to do. We don't need to burn electrons to know what to do next. We know what we're going to. We know what we're going to do next, like the Scottish country dancing that we saw earlier. So we can coordinate by time, on time, rather than expending energy on time-dependent dynamic values. Other advantage of static analysis: a circuit where you know cycle by cycle what it's going to do at compile time is much easier to reason and do a formal proof of that circuit. And that's something I care about very much. My last project was all about trying to formally design and implement, verify security circuits. And determinism, all the circuits we looked at were designed to have determinism as a property. The other advantage is getting composability. This is what lets us snap together multiple TSPs, and then we can say something about the execution of two bits of a subgraph on these two TSPs. We know that they could be in lockstep because we've got this deterministic compute model that makes it so. However, sometimes you would accelerate linear algebra using techniques more like hardware design rather than software. Often, often in hardware world, we're trying to make things look more like software. How can I make my hardware design more look like writing some C and pressing a button and having something good happens? But actually, there are situations where you actually want to have the control over timing that we typically have when we do designs in VHDL and Verilog. And I think this is one of the cases where you want to get extreme performance for machine learning models. You want to actually think a bit more like a Verilog engineer than a Java programmer. Determinism of formal verification is an advantage, and then determinism of power management is a very big advantage as well. I think it's a fertile area for future research, and I think there's lots of other analyses and abstractions that you can build as towers on top of us. So one thing we'd be very interested in doing is collaborating with universities. Perhaps you've got workloads that you care about trying to accelerate, machine learning, high performance computing, whatever. Maybe we should talk and see if we can map them onto our devices. Maybe you like doing tooling for HLS or mapping data paths onto FPGAs. I think a lot of that skill and experience actually can be applied to mapping to these TSP-like machine learning accelerators. So if that's something that you'd be interested in discussing, please email me at Groq or DM me on Twitter. I'd be very happy. I'd be very happy to talk to you. There's a paper. If you want to find out more about technical details, there's a paper called Think Fast, a tensor streaming processor for accelerated deep learning workloads from ISCA that you can Google and download from 2020. And I'll show you a picture which shows you, which tries to capture what's happening under the hood for a realistic TSP application.
Bring me a dream, they're gonna shoot it, that I'll never see. You'll have nobody to call my own.
Hair-raising stuff, but if you can schedule it well, nobody gets run over and there's no accidents. It's a very efficient use of the asphalt. Enough of that.
Okay.
So for more information, you can find, you can go to Groq's website or email info@groq.com. You can follow us on Twitter and on social media. And of course, we're a growing startup company and we're hiring. So do contact us, do contact me. So I'm happy to take any questions.
Okay, Senan, thanks for a very stimulating talk. Before we open up for questions, I want to mention that you showed a clip of Scottish dancing, which is fun, but the music was so loud, whatever you were saying was completely overwritten. That maybe
I apologize
you want
for
to
that.
deliver one to seven.
All I'm saying is each
messages.
of those dancers know what to do, and they know the next step they're going to take. And they're dancing with each other. And then these Scottish country dances can be quite elaborate. So you've got single chip country dances where it's just two people dancing. Then you've got multi-chip country dances where you've got several groups of people, and then they change partners and reconfigure. And every person knows what they're doing. They've got a static compiled plan, and they execute that plan in lockstep. And everyone executes a plan, and it all works out beautifully. So I think Scottish country dancing is a very good metaphor for this kind of deterministic compute that you get with TSPs, with one chip and with multiple chips, just like the intersection that you saw in that last video. That's the main point. No one is waiting. No one stops and waits for someone else to arrive, some arbitrary number of cycles. The other person's there exactly on time.
Great. If I can also ask, in this node, do you have any DRAMs, or it's all on-chip SRAM?
No. So on this chip, it's all SRAM.
Oh, SRAM.
There's 88 slices of SRAM.
Right, but when
that's what lets us be deterministic.
Yeah, when you compose them into bigger systems, that you have 8 cards, right, into a node, you can have many nodes into the system. Do you use any DRAM or no DRAM at all?
So I might say the wrong thing here because I'm relatively new to company, but I don't think so. Not on the current card. We have all kinds of exciting plans, and you can kind of imagine what they involve, but not at the moment. The primary memory is the 240 gigabytes of SRAM. That's in slices across the chip. And then if you want a larger capacity device, a computation, then you map that across multiple chips.
Okay, great. Thanks. We can take 1 or 2 questions from the audience that you can type into the message system, the chat. I'll be glad to relay the question. Otherwise, we'll end in 23 seconds.
And you know, I'm very keen to have collaborations, discussions. So feel free to contact me, and we can have a video chat and see if there's any way we can collaborate.
Right. Okay. In fact, if not, then maybe I can ask another question. Is that do you compare with the wafer scale integration, some of the efforts?
So right, you're talking about another company that does that. So
Exactly.
I'm
You know
sure
what
they do. I don't have I don't have the numbers for that. I don't know the numbers of that. I mean, that's a very interesting approach. It's a very, very different way of going forward, and I think they've made very different trade-offs. So that all seems interesting, but I don't have a comparison at my fingertips. I'm still trying to understand our own architecture.
Okay, great. Thank you so much for this stimulating keynote. We all enjoyed it. Right. Well, we hope to have more discussions offline.
Okay.
Thanks. That concludes the session. I think we'll have 10 minutes break, and then we'll be coming back to the poster session after that.